Here in video 22C, we address the force dependence of the state changes that cause yielding elasticity. To answer this question, we have to ask about the effect of force on the energy landscape. Recall before that without force, we have this energy landscape drawn here where state 1 is lower in energy than state 2. And we're now introducing this notation that we call the superscript naught, means standard conditions. That means without force. We'll now say, well, what happens with force? And we'll call this of F. We refer to this as of F, as in, now that we've introduced this notation, we'll notice that all of our previous definitions still apply. None of them said anything about explicitly what force. So they apply all of those things we talked about: the equilibrium force, the probabilities, the difference, referring to difference in energies, the definition of the difference in energies. Those can all be true in standard conditions or under force. Now we'll look at what the energy landscape looks like under force. So our force is altering the energy landscape. It's linear because the derivative of force, or the derivative of energy, is the force, and we're assuming here that we have a constant force. So we will define then that the energy is negative, that constant force, times x, the extension of the molecule. Now we add these two landscapes together. We add the landscape of the molecule to the landscape of energy pulling on the molecule to get the landscape of the energy of the molecule under force. And we just show that, I've shown that graphically, and here we show it mathematically, at least as it applies to each of the states, state 1 and state 2. Because this applies to both states, it applies to the difference between the two states. That is, the difference in energy between the two states at the force F is the difference in energy without force minus the force times the difference in extension at F. So in our drawing, that means that this distance here, which is the difference in energy under force, is equal to the difference in the two states without force minus the force times the difference in the states at that force. So I know this is challenging, but I've tried to provide here both a graphical picture of what this means, of how the energy landscape is being tilted or offset by that force to change the energy between the two states, and how that relates to this mathematical expression for how it changes the states. So now we want to use this. What we showed in the previous slide is that we end up with this equation that the difference in energy between two molecules in the presence of force can be determined by their difference without force minus force times the difference in length between the two states. And so what we're interested in asking now is the equilibrium between two states. So we can calculate the equilibrium constant, K equilibrium of F, just by exchanging in this value that we wrote above for the delta G at this force F. And so one of the questions we'll ask here is, at what equilibrium force, and we'll call this F equilibrium, at what F equilibrium do state 2 become equally likely as state 1? Because that's the force at which we start to pull this molecule into state 2. It was less likely before there, and above this force it's more likely. So we know that they're equally likely when the equilibrium constant is 1. And so we need to set then this value of the equilibrium constant to 1. Well, we know that an exponent of something is equal to 1 when what's inside the exponent is 0. The denominator is a set value, so to get the whole thing to 0, we need the numerator to be 0, well, including the negative, but it doesn't matter when you set it to 0. So this tells us that this thing inside must be 0 at the equilibrium force. So we'll rewrite that, since this is the equilibrium force, we'll rewrite that as F equilibrium. And this is our key equation that tells us the requirement for reaching the equilibrium, that the F equilibrium times the change of length at the equilibrium force has to equal the change of energy without. The way to think of this is the equilibrium force. This is the force at which the energy due to the force is equal to is enough to overcome the energy between the states, the difference in energy between the states without force. So more generally, in addition to asking about the equilibrium force, we might ask, what's the effective force on this equilibrium constant? So we had written above from here that the equilibrium force at F is this exponent of this. Now, you might recall that an exponent of two things that are inside the parentheses, two terms subtracted or added to each other, are just the sum or the product of the exponent of the first times the exponent of the second. So this is exponent to the minus delta G, which we had here, and then the minus and the minus make a plus. So this second one's a plus. But we might remember that exponent here of the negative delta G naught over kBT over thermal energy was just the definition of the equilibrium force constant without force. So the equilibrium with force is the equilibrium without force times the exponent of the force times the distance and length divided by thermal energy, which is to say that because K equilibrium of F is the ratio of the two probabilities, that the increase in the equilibrium constant means that state 2 increases in probability, and force is exponentially increasing this equilibrium constant as long as this thing that was inside here is greater than 0. So this requires that state 2 is longer, delta x of F is longer than delta. So that delta x of F is longer, which means state 2 at the force is longer than state 1 at that force, because we've assumed force is tensile. So that's what's required for the force to exponentially make state 2 more dominant. The previous slides depended on what is the difference in length between the two states at force F. And this depends on the elastic properties of the molecule in the two states. If we have linear elasticity with spring constant Ki for state I, then we can express each state as the sum of the state without force plus force divided by that spring constant. And then the difference in states is just the difference between the two at that. So we'll subtract the two distances without force, which of course is the difference delta x naught. And then we add together the differences in the force divided, or the force divided by the spring constants, and that creates this term here. And so this is our expression for delta x of F, the difference in force of extension at force F for linear states. Several substates are interesting. If both states are stiff, that means that the 1 over K2 and 1 over K naught are really small numbers, and F times them will be much less than the difference in length in without force. Sorry, there shouldn't be an F in there. So the difference in length without force. And in that case, you can just neglect this second term, and you can say that the difference in length at the force is around the same as it was in standard conditions. You can say the same things if the spring constants are identical, but then because then this term is 0, even if they were soft. So again, we get the same very simple expression. Now in contrast, if state 2 is an unfolded worm-like chain, and state 1 is stiff and force is really high, then your state 2 starts to approximate the contour length, and your difference in length is around the contour length minus state 1 in standard conditions. But in between the linear string approximation of a worm-like chain and full extension, the unfolded protein is complicated and you'll need a numeric solution in all likelihood. Now with this information, we can go back and ask about the equilibrium force. We said before that the equilibrium force satisfies this requirement that the difference in energy without force minus the energy created by the force between the two states has to be equal to 0. And so if both states are stiff or have the same stiffness, we had this very simple expression that the difference in length is the same as at equilibrium. If we plug that into this value here, we have this very simple expression here, and we can rearrange that to solve for the equilibrium force. That is, the equilibrium force is the ratio of the difference in energy to the difference in length in standard conditions. If instead at least one state is soft and the spring constant are different, then we had to use this linear term, and we need to plug this into this equation here. And when we do that, that expression becomes a polynomial because this had a force and we are multiplying it by a force. And so we have terms with force, force squared, and no force. The whole thing's a polynomial in F equilibrium, so we can solve for F equilibrium using the quadratic formula or a Roots command if we're using a computational approach. These two methods allow us to calculate the force needed to cause the molecule to switch from mostly state 1 to mostly state 2, recalling that that's the definition of the equilibrium force. So depending on information about the stiffness of the molecules, you can use one of these two equations. Of course, you have to do something much more complicated if you can't assume a linear spring. So finally, we revisit our original question about yielding. What's the relationship between the equilibrium force and yielding? We consider a fiber that has n subunits. We know that at F equilibrium, all of these subunits will elongate, and so the fiber will yield there. So if we draw a force extension curve, then we have at F equilibrium, this fiber will elongate. Before it starts elongating, it's just stretching at the spring constant of n of the x1 subunits. So what is the spring constant of them? And typically, we know that the spring constant of n x1s is around x1 divided by n, or k1 divided by n. So k of n of these. Remember, because you divide spring constants by the number of them when they're in series. So we have this stiffness here in the initial phase, and then we have the yielding. And as it yields, it extends from a length of n times x1 of F equilibrium until it gets to all n subunits are at state F2 at the equilibrium force. So it's extended that amount, and then it will start to stiffen again in whatever the spring constant or the elastic behavior of state 2 is, which is often for an unfolded protein a worm-like chain. So you can see how this quantitative model reproduces the behavior of yielding polymers introduced in video 22A.